It is a basic assumption of human biomechanics that scaling up a physical frame directly equates to scaling up physical capability. Taller translates to stronger. Evolution historically favors the middle ground, relying on the 5 to 6 foot range as a biological baseline. It operates as an incredibly versatile, generalist framework that handles heat, cold, and varied physical labor efficiently. But when you plot the extremes of human stature, a strange paradox emerges. The absolute highest raw outputs belong to the tallest among us, yet the highest relative efficiencies, the pure mechanical optimization of the body, belong to the shortest. To identify where these efficiencies peak, we have to look at the performance data of the compact phenotype, those falling into the range between 4 feet and 4 foot 11 inches. At this scale, the physical laws governing the body begin to behave differently. Shrinking the human skeleton changes the foundational mathematics of how it moves. To understand exactly why, we have to evaluate the human frame through the strict lenses of rotational kinematics, physiological scaling laws, and structural biomechanics. What the physics reveals is that human performance does not scale in a straight line. Instead, short stature functions as a highly specialized, mathematically optimized biological framework. To see where the compact frame excels, we first have to validate exactly where it loses. Larger human frames possess inherently longer lever arms. This structural reality maximizes absolute spatial reach and total stride length. This provides an undeniable absolute advantage in environments that strictly require elevation and vertical reach. It also allows a tall frame to maximize pure leverage and span across wide horizontal distances. But shortening that biological lever arm changes the foundational timing of human motion. Look at this 3D biomechanical model comparing a standard arm to a shorter one during a striking motion. The shorter limb inherently requires less physical travel distance for the distal points, the hands, to complete their structural arc. Because the hand has less physical space to cover, the time required to complete a single kinetic cycle drops. This allows the shorter arm to execute a higher number of cycles in the exact same time frame. Apply this exact kinematic principle to the lower body, and it dictates a naturally higher step rate cadence for runners of shorter stature. While a 6-foot frame easily covers more distance per individual movement, the 4-foot frame is biomechanically optimized to produce higher movement frequency and rapid physical cadence. This mechanical efficiency becomes even more apparent when the body leaves the ground. The primary barrier to spinning in midair is rotational inertia, the body's natural physical resistance to angular acceleration. This resistance is governed by a precise equation, I equals mr squared. This visualization calculates the inertia of a gymnast positioned in a layout pose. Notice that the radius, represented by the glowing line from the center of mass out to the extremities, is squared. That makes the length of the limbs the single most critical variable in dictating rotational speed. Watch what happens when we scale the proportions from a 6-foot frame down to 4 foot 5. As the radius line shortens, the total window of inertia drops exponentially. This smaller window of inertia means shorter individuals generate higher angular velocities using the same amount of applied force. This physical reality explains why highly compact frames consistently rule gymnastics, why competitive diving demands a tightly tucked radius to maximize midair spin, and why elite figure skaters rely on pulling their mass tightly inward to hit terminal rotational speeds on the ice. In high-level acrobatics, operating within the 4-foot range functions as a structural requirement dictated by the laws of angular momentum. Beyond the kinematics of motion, we also have to look at the geometry of mass. Specifically, how volume and surface area scale disparately within the human body. As this visual demonstrates through the square-cube law, when an object scales up, its surface area scales squarely, but its total volume scales cubically. When mapped onto human muscle tissue, a critical imbalance occurs. Muscle power is determined by its 2-dimensional cross-sectional area, but the body has to continuously lift its own 3-dimensional volume. Notice how the larger torso's volume vastly outpaces its sheer lifting power. As height decreases, the body sheds its total volume faster than it sheds its cross-sectional muscle area. The result is a mathematically superior strength-to-weight ratio. This ratio manifests constantly in competitive weightlifting, where highly compact frames successfully lock out massive, absolutely disproportionate amounts of physical weight. Scaling down total body volume lowers the baseline caloric intake required to sustain the organism every single day. This shifted surface area to volume ratio directly alters thermoregulation as well, providing greater heat retention capabilities in cold environments. And if we push this volumetric scaling all the way down to the microscopic level, a smaller total volume dictates a lower absolute number of cells in the body. With fewer total cells dividing over a lifespan, there are statistically fewer opportunities for unexpected cellular mutations, resulting in a naturally lower risk of cancer. By obeying the square-cube law, the 4-foot frame operates as a hyper-efficient biological machine, maximizing structural strength while minimizing caloric cost and cellular risk. However, biomechanical scaling operates on a strict bell curve. There is a rigid physiological floor where the structural system simply breaks. When the human frame drops below 4 feet, specifically entering the 2-foot to 3-foot 11 range, the mechanical advantages vanish. At this scale, the severely reduced frame is almost exclusively associated with the pathology of extreme dwarfism. Watch the structural model as the height drops from 4 feet down to 3. The highly stable skeletal structure becomes violently constrained, as efficiency markers instantly convert into severe visible stress vectors. A primary constraint is spinal stenosis. The vertebrae compress so tightly together that they physically pinch off the nerve roots, crushing vital neurological pathways. The systemic disadvantages compound rapidly from here. Extreme bone density causes joint deformities, constant chronic pain, and dangerous obstructions like sleep apnea. Internally, the cardiopulmonary system becomes entirely trapped within a compromised cavity. The resulting organ stress aggressively depletes the overall lifespan of the organism. Below that 4-foot threshold, structural and neurological failures override the mathematical advantages of scale. The human scale spans a massive operational spectrum, from the 7-foot colossus down to the compact 4-foot frame. This data screen illustrates the structural trade-off inherent in human biomechanics. You cannot optimize a physical structure for both absolute force and relative efficiency simultaneously. Exceptionally tall statures will always dominate physical arenas that strictly demand absolute leverage, the manipulation of pure total mass, and maximum spatial reach. The 4-foot frame defines the upper limits of relative efficiency, yielding advantages in cadence, rotational kinematics, and strength-to-weight mechanics. Biological design is not infinite. It is strictly governed and bounded by the uncompromising laws of physics. Physics defines short stature as a mathematically optimized solution for complex physical movement.